So is my screen visible?
Yes, sir.
Okay. So this problem is formally called as frequency estimation problem. So I'll just start with uh, say some notation, and then we'll see a toy problem, and we'll see some naive solution, and then we'll finally see an elegant solution of the problem. So I'll just state a notation. So suppose we denote our data stream as sigma, which consists of elements A1 to AM, and each AI, which is element of the data stream, is drawn from a universe U of size n. And for simplicity, we assume that this U is set of integers, right? So for example, in case of URL, we can map URL to uh, one integer number. So this AI belongs to set 1 to n, and this set 1 to n will just briefly write it as n. Okay, so our data stream consists of m elements, and each element is belongs to an universe of size n, and which is basically a number from 1 to n. So we one example. So suppose our universe is alphabets, and our data stream is maybe like this: A, B, A, B, B, C, C, D, E, F, G, and so on. Right. So this is our data stream, but the constraint is that each element of the data stream is an alphabet. Right. So universe is alphabet. So our aim is to prepare a data structure so that basically we'll take a pass over the stream, update our data structure, and then using that data structure only, we need to give an estimate on the frequency of some element in the stream, right? So for example, we want to count how many times A has appeared in the screen, in the stream, using that data structure. So this is our problem statement. So is this clear to everyone?
Yes.
Design data structure or sketch that estimates frequencies of query items, right? So is the problem statement clear? Okay, so in Bloom filter, the problem statement was whether a particular element was present in the stream or not. here is somewhat basically a next level problem. Here we want to estimate the frequency of a particular item. And in Bloom filter, what we used to do, our data structure is a bit array. And in that bit array, we initialize it with all zero. And once we see a item, we just calculate it hash values and update the corresponding position as well. So here, any intuition what modification we can do on Bloom filter so that it solves our problem?
So we can use a map or a dictionary to keep count of the you know, URLs or the alphabets.
Okay. So, okay. So basically one naive solution is basically generate an array of size u, which is n, and upon arrival of an item, increment the corresponding position. Right. Initialize initialize with all zeros. So basically we generate, uh, take a bit array, initialize it with all zeros, and then basically upon arrival of an item, we just increment the corresponding counter. Right? And then when we need to find the frequency of a item, we just go to the corresponding position and check the counter. But again, needless to say, this is not very efficient solution because it requires space of the size linear in the universe. It's not space efficient. Size equal to universe size. Okay. Now again, we want a space efficient solution based on universal hash functions. So what can we do? So can we borrow some idea from Bloom filter? Okay. So in Bloom filter, what we generate a bit array, and suppose we have, okay, so in this I'll
So,
take this in, yeah. Yeah, say
can
that again.
can we keep the counter instead of one? Can we keep counter there?
Yes, exactly. This is what we are going to do. Okay, so I'll just try to elaborate this with one example. So this was our example. Maybe so it's A, B, A, C, C, D, E, F, G, and so on. Okay. So again, we'll use a hash function that maps each these elements, say A, B, C, D, E, F, G. Suppose this is 1, 2, 3, 4, 5. So suppose this hash function h maps A to second position over here, maps B to third position, maybe here, maps C to first position over here, and maps D to maybe second position. And again, we can assume that the size of this is smaller than the size of universe, right? So we cannot avoid collisions, and we'll see how to handle those collisions. And suppose E maps to here, F maps to maybe here, and G maps to here. Okay. So initially, all of them were initialized to 0. So now once we see this element, A is mapped to second position, we'll update the counter by 1. B, we see B over here, so we'll update the counter over here. We again see 2 A's. So we'll just increment this counter by 2. So this is 1 plus 2, 3 now. Again, we see 2 B's over here. So again, we update it to 3. And then we see 2C. C is over here. So we update it by 2. Then D. So now we see that both A and D are mapped to same position, right? So for D also, we need to increment this counter. Right. Now for E is comfortably we can put over here. For F, again for F is also mapped over here. So for F, we need to increment this counter. And G, we can comfortably put 1 over here. Okay. So again, the idea is similar to Bloom filter, but the only difference is we increment counter every time we see the corresponding element. But here, what is the problem? There could be some cells in which more than one elements are getting mapped. And in that cell, the counters of basically the frequency of those elements will get added. That will produce the error, right? So is this part clear?
Yes, sir.
So what we can do now?
Sir,
Yeah.
in the previous case, we were using multiple hash functions, right?
So here we are using one hash. So far we have used one hash function, but we'll see that there is a problem of collision. Like so what we can do? Okay, so even until this part, so suppose basically this is our sketch. So when I say sketch data structure, essentially it's kind of one kind of compact or succinct representation of input, which solves the corresponding problem. Okay, so if suppose until this part, this is our sketch, and if we want to estimate the frequency of A, so basically what will be our algorithm, we'll just see in which bucket A has been mapped, and we'll just look at the corresponding index, and whatever counter is there, we'll just report that counter, right? So frequency of A will be 4 as per this example. but there is an error due to, because D is also mapped in the same cell, and which increments the counter of A by 1, because D has appeared 1 in the stream. Okay, so we want to minimize this sort of error. So what can we do?
We can take the minimum across all the.
Across what? Yeah,
Across the
you are.
hash function. So basically, so wherever it is pointing to, like, yeah, I mean, what I mean to say is like calculate the hash and then it will point to 3 different locations, right? 1, 2, or 3, like that, and then take the minimum across them.
Not really. So because here A is pointing to only one location, this second cell, right? So for in this data structure or this sketch, we get only one estimate of A, that is 4. Basically, whatever value was there in that cell.
And this sketch, whatever we are writing, is like a single integer, or it is like a list of integer.
So it's a number. So if you want, I can just. So this is basically 1 plus 2 plus 2, which is 4. So in this bin, we'll have 4. So this will have 4. This will have 3. This will have 2. Right. So finally, this will be our sketch.
So can we
huh?
calculate the probability of the collision and subtract that from whatever number we do?
Yes. So that will do to analyze how good our algorithm is. But now we can do some more things so that error can be minimized, right? So basically, first we'll try to come up with an algorithm in which error is minimized, and then we'll just try to analyze that algorithm, right? So our first step is like, just can we define this algorithm a bit more so that the error due to collision can be minimized.
So here we are using only one hash function, right?
Yes. So what can we do?
If we can use multiple hash function and then take the minimum, it will be possible.
Okay. So,
or we can take 2 hash function and create a 2D map sketch.
right. So this is what this is the idea of this algorithm, and I'll just try to elaborate it. Okay, so this is one hash function. Say maybe let me call it as say h1, and I'll prepare another sketch on the same data stream using different hash functions. Say maybe h2, right? Again, h2 will map each of these elements, and h2 is different from h1, but both of them are sampled from the same universal hash family, right? So basically, corresponding to each hash function, we'll get this array. Suppose this is correspond to h2, and again we can come up. Basically, we choose another hash function which give another sketch. Maybe we take another sketch using different hash function, maybe h4, and each of them are sketch of our this data stream, right? So now what? So suppose you repeat the same thing 4 times using 4 different hash functions. Now suppose our aim is to find the frequency of A. So using these 4 sketch, we'll get 4 estimates of A, right? Basically, the algorithm will be, we'll just go to the corresponding position. So suppose in this place, A is mapped to this position. So A is mapped to this position. In H3, A could be mapped to this position. And in H4, A can be mapped to this position again, right? So we'll get 4 different estimates of A, right? Now, which one should we choose?
Can
Or
take the
how-
minimum of
Yes. Why minimum?
that way we will avoid if there are collisions that will add to the counter, right? And taking the minimum will ensure that we'll not take the instances where there was collision.
Right, right. So exactly this is what we'll be doing, and this is very classical algorithm of uh, in streaming algorithm, and this is called count min sketch, and this was
Sir, will we be having the track of where A is bucket or binned or in different?
yes. Yeah, so that track we keep via this hash functions, right? So this hash functions, what they do, they take this element and map to, maybe suppose this is say M, so they map to this M, right? So these hash functions take this element of the stream and assign it to one of the location in M.
Okay, sir. Yeah. Thank you.
And this algorithm was count min sketch and proposed by Graham Cormode and Muthu Krishnan. It was appeared in 2005. And this is again very simple and elegant algorithm for a very fundamental problem. And it also used quite a lot in practice as well. And the idea is essentially what we have discussed so far. Right? So basically prepare a counter sketch of using hash functions, repeat the same experiment several times, and each repetition gives one estimate of estimate of the frequency, and we take the minimum, right? So this is the algorithm, and you are able to come up with this algorithm. So that's good. So now the thing is, we need to fix several parameters, right? So how many times do we need to repeat? So suppose how many times we need to repeat. So basically, this is, suppose we call MST, and here I'm using slightly different notation. So this is, I'm calling as K. Okay, so K is our size of sketch and T is the number of times that we are repeating, right? So how to choose K and T? Appropriately. Okay, and essentially this is a 2-dimension array, right? Right, so this is a 2-dimension. Our sketch is nothing but 2-dimension array where each row correspond to different hash functions chosen from same hash family. Right, so suppose if we get say some element A, so this H1 will map to some position. Right, so due to H1 suppose map it to this position, H2 maps it to, for example, this position, HT maps to this position. So basically on these places, the corresponding counter will get implemented, right? And suppose on the query time, we'll just probe the corresponding cells, see what numbers are there, aggregate all of them and report the minimum, right? So is the algorithm clear to everyone? And
Yes, sir.
these HIs are from sampled from universal hash function. Okay. So again, the algorithm is simple. Now our main aim is to analyze our algorithm. Basically, how to choose this K and T appropriately so that we can give some guarantee on our estimate, right? So how to choose K and T appropriately such that error in the estimation is small. And when I say estimation, I mean frequency estimation. So our all right, so we'll just try to analyze our algorithm. So our notation, what we used, yeah. This AI belongs to. Fine. Okay, so I'll use this notation, say Fi, to denote frequency of, say, item I. Okay. So suppose A is our query item. And its ground truth frequency is FA. Basically, the actual frequency in the data stream is FA. And let FA hat denote the frequency reported by count min sketch. So for brevity, I'm writing this CMS, count min sketch. Okay, so FA hat is the estimated frequency of query item A, and FA is its ground truth frequency. So what can we say about FA and F hat A? So FA can be bigger than F hat A.
Yes, sir.
FA is the ground truth actual frequency, and F hat A is the frequency reported by this count min sketch algorithm.
No.
So FA should be at most F hat A. So are you agree on this point? Yeah. Because in this example, there could be, it's possible that more than one items map to same bin. So basically, for example, in this bin, it consists the count of both A and D, right? So this will this will give us an overestimate. And although we are repeating it, but even after repetition, it can be as good as FA, but not smaller than that, right? So F at A will always be bigger than FA. Right. So I hope you are with me on this point. But now we'll just try to quantify how big F at A is with respect to FA. So F at A is FA plus some error term. And how is this error term coming up? So can we just quantify this error term? So basically, the error term is because some different element which is not equal to A is mapped to same position in which A has been mapped to, right? So basically, all those elements which are not equal to A, but they map to same position in which A has been mapped. So basically, their frequency count will be the estimate of the error term. Yeah, tell me.
Yes, so the probability of those hash functions incorrectly
Yes, yes, yes.
hashing to that location, right?
So this error term is basically sum over all those J's which are elements of our data stream which are not in A, right? So here I'm just quickly recall the notation. This data stream is this AM, where this AI belongs to N, which is our universe. And I'm also using this J belongs to N as element of stream. Right. Okay. So all those element in the stream which are not equal to A, basically these are the set of elements in the stream other than A, and their frequencies are denoted as Fj, right? Which map to same position in which A has mapped, right? So I'll just quantify this by an indicator random variable, and then I'll just explain it in a minute by Yij, where Yij takes value 1. If Hi of j is equal to Hi of A. And if right. So for example, if say some element j, which is some element, say maybe j, which is not equal to A, and it has mapped in the same bucket in which A is mapped in the hash function Hi. So for that, the Yij will be 1. And for that, Yij will be 1, and their corresponding count, Fj, will be added in the count of A. Right? And but for all those, say some j, maybe say j1, which is not equal to A, and but for that, Hi of j1 is not equal to Hi of A. So their Yij, ij1 value will be 0. So basically their frequency will not add up in this error term. Right? So is this expression, like, are you able to follow this expression?
So basically we are saying that if for a particular element in the stream, and the hash matches with the element A, only
Yes.
then this indicator variable will be incremented
1.
or 1.
So in that case, indicator random variable will takes value 1, and if
Yeah.
this is 1, then the frequency of that particular item will be added in the frequency of it.
Okay, so this will be 1. If we are calling this as the error term, it's basically counting the false positives.
Maybe false positive may not be correct term. So it's basically we need to report some number, the frequency of A, and there is some error, and we are just trying to quantify that error. Right?
Okay, sir. Okay, sir.
Yes. So is everyone with me on this point? So this may look somewhat tedious, but essentially the idea is very simple. Okay.
So, but that will result in false positive only, right? Because we are looking for the exact count and we will not get the count because of this error.
So false positive we defined slightly differently. So false positive in our previous case, basically when we need to report yes or no, right? So the element which was not present and we are reporting them as yes, then that is false positive. And this is error in estimation. In this case, our problem is to estimate the frequency of a query item. So what is the error? In our algorithm, we just try to quantify it. So false positive may not be appropriate term here. So basically the error in the estimation.
So here the errors would be like more of like how accurate is my
Yes.
number? How close is it? Okay.
Yes. So this error is other elements hashed in the same location where A is hashed. And suppose we are denoting, yeah.
One doubt I'm getting is like, so like generally in Bloom filter, so once we get the false positive, so the implementation, how it happens is like, we'll capture this, we'll add this Bloom filter in the client side, and then we understand that this is false positive, and then we hit the server to actually identify whether it is correct or not. So that way, the application side, right?
Yes.
So there is a validation always in the server side as well, because we cannot afford to make mistake. So in this particular case, how like once we made a false like error, then how it will go? I'm not understanding.
So here I think
Or is it like always for an error we will have to calculate it?
yes. So basically here our aim is to basically choose T and K, basically the size of array, so that the error is below certain threshold. So this is how the kind of guarantee we can give. So basically, if you choose this much of T and this value of T and this value of K, the error in your estimation will be less than this with high probability. Something of this sort we can guarantee in this setting.
Okay, got it.
So we don't have we do a theoretical we give a theoretical estimate, right?
Yes.
Okay. Sir.
Yes, so that's what we are going to do now. Okay. So suppose I'm denoting, so this error due to hash function hi, right? And I'm denoting this error term by xi. So this xi is sigma fj yij, where j is in n minus a. Okay. So this is again a random variable, and we would like to compute its expected value, or basically some statistical measure. So we'll just try to calculate it expected value. Okay. So by linearity of expectation, I can just take out these FJs. So what is expected value of Yij? So I'll just write one more. So what is Yij? It's expected value of Yij. It's probability that Hij is equal to Hia. What is this probability? So remember the size of sketch here. This is K.
One by K, right? So
This is 1 by K, right? So as per the definition of universal hash function. So this is summation Fj upon K, where J is from n minus. Right. So I'll just use one notation. L1 norm of F as F1 plus this. Right. So this I can write as L1 norm of F minus Fa upon K. Right. And this for brevity I denote F minus A. So this is notation, nothing fancy. F1 minus Fa. Okay. So this is, so I'm just rewriting this in a different notation for convenience. Okay, so our expected value of xi is okay.
So one question, sir. So
Yeah.
here, when in the notation, we are subtracting Fa.
Yes. So this is the summation of all j's which are in the universe except a. Right. So this will be
Oh, okay. I got it. Thanks.
by definition. Okay. So this is the expected value of the error in our estimation, and we'll just try to know how much deviating it with respect to its expected value, right? So we would like to know what is the probability that xi is more than epsilon times f of minus a.
Markov.
Yes, so we'll apply Markov, right? So Markov inequality is probability that random variable, non-negative random variable value x takes more than one is at most expected value of a by. So this is what we'll be using over here. And this is E of xi by epsilon times f minus a. Okay, and just putting this value over here, we'll get f of minus a L1 by k to epsilon to f of minus a. So these two will cancel out. So this is 1 by k into epsilon, right? Now we choose k as 2 over epsilon, right? So if we choose k as 2 over epsilon, we're putting it over here, we'll get probability that xi is more than epsilon times f of minus a, one is at most half, right? So this statement says that, okay, if we choose k, basically this size of our hash function, size of our this array as 2 over epsilon, then with probability at most 1 upon 2, our error will be larger than this. So xi denotes the error due to hash function hi, right? So are you with me until this point?
Yes. So here it doesn't depend on the size of k, right?
No, it depends on the size of k. So basically here, so there is one parameter epsilon here, and k depends on this
Oh yeah,
epsilon,
2 by k. Okay.
2 by
Okay.
epsilon.
Yeah.
Now
Any
we,
specific reason
yeah.
of choosing 2 by epsilon?
No specific reason. You can choose take any constant. So finally, so if you choose maybe say 10 over epsilon, you will get 1 upon 10, right?
If I choose one option, 1 upon epsilon, then it is less than 1, right?
Yes, but in that case, k will be, yeah, so what if you choose k as 1 upon epsilon? So this will be 1, right? But so this is, just notice that this is an error term. This is kind of bad event, and we want the probability of this event to be very small, right? So this is, we want this to be sufficiently close to 0, right?
Yeah.
Right. So if we choose, as you say, k as 1 upon epsilon, then that may not be good. So basically, we want to boost this probability to say some delta, where delta is like very, like for any delta, like we can choose any number, any delta which is sufficiently close to 0, right? Right. So this is for one hash function, right? So this is xi corresponding to error due to hash function hi, but we are repeating this experiment t times. So basically what we did, we created a 2-dimension array of size k and t, right? And one hash function gives one row of this 2-dimension array, and we are repeating it t times. So this is maybe, so this equation 1 is for one such counter, but we have T such counters. Independently generated using H1 to HT, right? So the probability that, so this Xi is what? Xi is error in the estimate, basically F at A minus Fa. So this is how we defined our Xi, right? So the probability that F at A minus Fa is more than epsilon times F of minus A L1 is what? Is the probability that minimum of these Xi's, X1, X2 to Xt, is more than epsilon times F of minus A. Right? So basically we take the minimum of the estimate obtained from each of these rows. Right? So if the minimum is at least this much, then we are good. And since all of these repetition is done independently, so this is I from 1 to T, probability that Xi is more than epsilon times minus A. Right? And this value is at most 1 over 2, and we are repeating it T times, so this value will be at most 1 by 2 raised to power T by equation 1. Now if we choose T as log 1 by delta, or maybe order of log 1 by delta, then this is at most delta, by just putting T and choosing the constant term appropriately. Right? So
Sir,
yeah,
in the line where we are multiplying the probabilities,
Hmm.
should it be strictly greater than or equal to? Because in the previous line you've written greater than or equal to.
This line, so this line is fine. From this to this is fine, and from this to this, so all these events are independently generated. Right? So all these values in the rows are filled by independently sampled HIs. So this should be multiplication.
Yeah.
Okay. So okay. So finally, just to summarize, thus if we choose T as order of log 1 by delta and K as 2 over epsilon, or maybe probability order of 1 over epsilon, then with probability at least one minus delta, we have, so our estimate F at A will anyway bigger than FA, like at most FA, and on the right side it could be at most FA plus epsilon times F of minus A L1. Right, so this guarantee we can give. right? So is this part clear to everyone? Right, so this inequality should be fine, because anyway our, no matter how many repetition we do, our estimate will be like at least FA, and this term we get due to this. So this shows that with probability at most delta, the difference in the estimate will be this much, and we just use the same thing over here. Okay, so this is the guarantee of our estimate. Count mean sketch algorithm. So any doubt? Yes or no? Like if you missed any point, just let me know. Or if you understood, just say yes.
This is the complexity part.
Complexity part is yet to do. So I'll just, okay.
So here we are choosing
Two parameters, T and K.
T and
Yeah.
okay. Yes.
So our space complexity is basically the space required to store our sketch and storing the hash function, right? So the first thing will be storing T hash functions. How much space do they require? It's T log n. So essentially, storing a hash function is basically storing a number like these AIBIs that we did in the first session, and storing those numbers will require log n space, right? So storing T hash function will require ordered T log n bits. And the second thing is storing the count, storing the two-dimensional array, so T cross K sized array. Right. So so note that as per our notation, so these our notation. Yeah. So there are m element in our universe. To store an element of the universe will require log m bits. So essentially, storing one counter of that array will require log m bits, and there are t cross k such counters, so we require order of tk log n bits. So the total space will be order t log n plus order tk log m, which is order tk log m plus log n, and we'll just put the value of t and k over here. So it is order 1 by epsilon for k, and for t it's log 1 by delta log n plus log n. So this is the overall space complexity. Okay, so just to summarize, here we generate a two-dimensional array of size t and k, one row corresponding to each hash function h1 to hk, and we generate a hash function. Basically, we sample a hash function that maps the element of universe to one of the position from 1 to k. And so we randomly sample t such hash functions. And upon looking at the element of the stream, we hash each of the element and increment the corresponding counter. And to query a particular item, to estimate the frequency of a particular query item, we'll just hash them using the same hash function h1 to hk. We go to the corresponding counter, and the number mentioned there are their frequency uh, estimates of the frequency of the query item. So we get t such estimates, and we report the minimum of all of these t estimates. And if we choose t as this and k as this, then then with probability at least 1 minus delta, we get this much guarantee on the estimate of the estimate reported by the algorithm. And the space complexity is this much. Basically, which is storing t hash functions and storing t cross k sized array, which is overall is this much. Okay, so that's all I had for today. Any questions so far? Okay, so